Hello, everybody. Welcome to today's crime seminar. Today we have two speakers to talk. Our first speaker is Anuj Kumar. He will be giving a talk on efficient and physically consistent surrogate modeling of chemical kinetics using deep operator networks. Anuj Kumar is a fifth-year PhD student in mechanical engineering at North Carolina State University, focused on accelerating turbulent combustion simulations using data-driven methods. He recently completed an internship at Oregon National Laboratory, working on neural ODEs for modeling safe chemical kinetics. Anuj holds a Bachelor of Technology degree from the Indian Institute of Technology, Kanpur, India, and his research includes developing surrogate machine learning models for chemical kinetics as well as reduced order modeling of turbulent combustion. With that, please join me in welcoming Anuj. Anuj, the floor is yours. Now you can begin your presentation.
Thank you so much, Nazanin, for such a nice introduction. I'll start with my presentation, which is on efficient and physically consistent surrogate modeling of chemical kinetics using deep operator networks. So most of us are aware that advanced design of gas turbines and combustion systems is critical for decarbonization of power generation sector. And this design process is basically accelerated by CFD simulations. However, these CFD simulations are quite computationally expensive, and especially for turbulent combustion systems, where we have large number of grid points for a full-scale system. And then we also have a range of time scales and length scales present in the problem. In addition to that, we also have an interaction of multiple physical phenomena such as combustion, turbulence, transport, heat transfer, etc. On top of that, solving for the detailed chemistry in turbulent combustion is the major bottleneck. And that is because of the ODE associated with chemical kinetics is highly stiff in nature. And second, the dimensionality of the system is very large. So there has been some effort to accelerate the chemical kinetics. And so essentially, this is the ODE system we have, and so the system is represented in most simplest form, and the dimensionality of the solution vector is Rn is n, and then the for a practical fuels the n goes from hundreds of thousands, and it becomes quite computationally intensive to solve these ODA systems. So there has been effort to reduce the reaction mechanism size either through classical graph-based reduction methods or through principal component analysis or through reduced order flamelet models. There also has been effort to accelerate the chemical kinetics process through data by finding efficient surrogate machine learning models. So these efforts are mainly focused in three areas. First is the modeling the source terms part of this OD system. So in that, the neural network is trained to approximate the source terms of the OD system, and says that the loss function is essentially minimizing the predictions from the actual values. And during the inference, we need to actually use an OD solver to get the solution vector out of these source terms from the neural network. So this framework is actually good for only short-term horizon. After certain times in long-term horizon, the predictions become quickly unstable. And this is also limited to simpler fuels. The other approach is actually to learn the projection part. So we can we can input a state vector, and the output would be a state vector advanced by certain delta t. In most cases, this delta t is fixed. There has been effort to input delta t as a part of input as an input to the network, such that we can have a variable delta t, but those approaches are not successfully implemented. The more recent approach is modeling this OD system via neural OD framework. So where again the source terms are approximated using neural network, but the loss function is based on actual state vectors, not based on source term. So now the OD solve would be used during the training process, and this will utilize source terms as well as the initial condition to find the integrate the and find the state vector, and then this predicted state vector would be minimized against the actual ground truth data. So with this approach, we are able to have flexible time stepping part, and also the predictions are quite stable in long-term horizon. But there's one drawback. So let's say if the system is able to learn proper neural ODE or the proper dynamics out of the system, the stiffness remains there with the model. Since during the inference we are using an ODE solver, because of the stiffness, the computational saving getting out of this model is not huge. So essentially, what do we actually want? We want to have reliable predictions in long-term horizon. Uh, we also want to avoid the computationally intensive OD integration because of the stiffness, and that is the major. This is where the major cost saving comes into picture. Additionally, we want to advance our solution vector at a variable time step, so that our aim is to actually integrate this whole surrogate model to a CFD solver. And generally, CFD solvers have a demand or the requirement to advance solution vectors at a variable time step. So this needs to be fulfilled in order to integrate with a CFD solver. We also want to decrease the dimensionality of the system such that the framework can be easily extended to a larger field system or complex fields where we have the dimensionality of the system is quite large. We also want to advance solution vector in physically consistent manner. Again, this eases the process of integrating with the CFD solver. So our approach based on DeepNet attempts to address all of these issues. So before moving on to our approach, which is based on DeepNet, I would like to reiterate what is actually is deep operator network. Most of us are familiar what is deep operator network, but uh, I'll just reiterate it. So deep nets or deep operator networks are based on universal approximation theorem for operators, which states that any nonlinear continuous operator can be approximated to the desired accuracy if the parameters are present in this form. And based on this theorem, the architecture is such that we have two networks, branch net and trunk net. The branch net takes certain input function. The network operates on that function, gives us the transformed version of the function. And the trunk net takes the query point or the input locations on which the transformed version of the function is evaluated. So by construction, this can approximate any nonlinear continuous operator to the desired accuracy which we want. Before moving on to our approach, I would like to point out there are two works which have used DeepNet for chemistry integration. The first is from Venturi et al. So where they have uh, incorporated DeepNet model for chemistry integration says that the initial conditions go to the branch net and the solution vector at any instant in time is mapped such that the times on which we want to evaluate goes to the trunk net. In addition to that, they have used a shift net. Shift net essentially finds an optimal scaling for the input to the trunk net says that the overall architecture of DeepNet is a smaller version now. This approach was limited to simpler fuel. I think they have applied to hydrogen combustion mechanism, which is for with 19 species. And this kind of represents the starting point of our work. In parallel to our work, there has been work from the Crunch group as well on integrating chemistry, accelerating chemistry with using DeepNet, where solution vector at any instant in time goes to the branch net. And the discrete time steps are input to the trunk net, and we get the advanced version of the solution vector. This also utilizes partition of unity constraints on the output of trunk net. And it has been applied to pollute problem with 20 species and syngas with 11 species. So our approach of chemistry integration with DeepNet, we call React DeepNet. Instead of training it on the whole solution profile, we train React DeepNet in Windows such that there's all the solution point on trajectory can act as an initial condition, and there would be a corresponding window to be learned. And in this framework, any solution vector on the trajectory would be input to the branch net. The time step by which we want to advance. Actually, the time step goes from 0 to the window size, how large the window is, will be input to the trunk net, and we'll get the advanced version of the solution vector or the projected by.
Anuj, I have a question here. So
Yeah.
the capital delta T, is that the CFD time step?
We aim to have that a CFD time step or even larger than that, so that so this kind of represent the smallest time scale we can, the largest time scales we can integrate by which we want to have an integration in the CFD solver. So yeah, yes, kind of like on the same range of CFD time scales.
Same. Okay, thank you.
So during the inference process, essentially will be the solution vector would be advanced by small delta t's, and that delta t's can range from 0 to large delta t. And this inference of the solution vector would be in autoregressive fashion, such that the output would be again input to the solution operator, and it will keep on going for the whole rollout, and we'll get the whole solution profile along the trajectory. So this fashion, actually, as DeepNet is the operator learning framework, learns the actual integration operator corresponding to this chemical kinetic system. Now we focus on the architecture of DeepNet. In addition to branchnet and trunknet, we also have small networks like ShiftNet and ParamNet. So Shift is basically borrowed from the work of Venture et al. And finds an optimum scaling for the trunknet. In addition to the ShiftNet, we have added another trunknet, which we call ParamNet. So this basically informs the network about any parametric dependence on of the ODE system into the network. And these parameters could be either equivalence ratio or initial conditions like initial temperature or pressure or volume of the system, depending on what parameter which we want. And these parameters are generally unique for a particular trajectory. This parameter also acts as a residual connection, such that like it takes the information of initial condition of parameter and doesn't let this solution vector diverge when the solutions are being predicted. And here the output are again like a dotted product, as it is dotted from trunknet and branchnet. So there is like additional dot product with the paramnet.
Anuj, why can you not have that in the branch, for example?
One of the input here, like as a parameter.
Yeah, yeah.
So generally, like these parameters are, I think, are like fixed for a trajectory, and here the solution vectors are evolving.
Continuous. I see. So the paramnet is keeping track at the connection points, right? At the jump points, right?
Yeah. So it is like
to
it is kind of fixed for whole trajectory. However, the solution vector is getting changed in these inputs.
Right, but the time scale for the paramnet is the capital delta T, so to speak.
Time scale for paramnet is rather like full trajectory. So like this is same for whole time profile.
Right. That's what I mean. But it goes from the CFD time step to the CFD time step.
Yeah.
Okay. Thank you.
Mm-hmm. So then we move on to the training part of React DeepNet. So as I mentioned, any trajectory or any solution point can act as an initial condition here. And then for that initial condition, we'll have a window for which the solution needs to be learned. So in this fashion, we'll have all the points on the trajectory would be input to the branch net. And then corresponding delta t's would be like these would be the delta t's, so this dt, then 2dt, and this it will cover the whole window through this input of the trunk net. And then correspondingly, we'll have output from the network. And then these the input would from the parameter would be parameters which are unique to these trajectories. So in this fashion, we have total number of points, like total number of points in the trajectory times total number of points in the window and total number of trajectories itself. And accordingly, we have a loss function that is based on what are our predictions and what is the actual or the ground truth data we have. So once this early training part is done, we move on to the refined training part. So here again, these here in the during the training itself, we are performing these auto-regressive steps, and says that so the output of network again is fed to the network, and says that we get a more advanced version of the solution vector. So let's say we have phi of t, the output would be phi of t plus delta t, and once we input this to the network, will be the solution vector would be advanced by 2 delta t. And this auto-regressive rollout can be done for L times. So we'll have solution vectors at each step. And corresponding, we can formulate the loss function at each step as well. So the total loss would be summation of all these points. And in order to keep track, so now the training data is getting enlarged. We just randomly downsample or NP, NS, or those like number of points on the solution vector or number of points in the window, such that the training data is tractable. So once we call this loss function, which is summation of all these loss functions on individual points, a long time loss function. And the training is done in, again, in gradual fashion. So first we do this training for, let's say, 5 autoregressive steps. And then once it is done, we move on to 10 autoregressive and 15. After certain step, we start getting diminishing returns. So it doesn't make additional benefits to the network. One might argue that why don't we directly train for 15 points, let's say, instead of doing early training and then 5, 10. So the early training part is necessary because directly integrating for 15 points is the training process highly unstable and the loss doesn't decay well. So it needs to have a good starting point, and those starting points are provided through the early training. And that is essentially L equal to 1. And then we can keep on increasing these autoregressive steps.
Excuse me, can I ask a question?
What's your typical value of NL? Sorry, I interrupted. The typical value of NL.
Here we have done it for 15 points. After 15 points, I did not see any extra benefits getting out of the network. But this is for when I'm integrating for a 0D problem, let's say. Currently, I'm also been working on a turbulent data set where any points can act as initial condition, and then all those points are evolved in Cantera. For those points, we have NL goes up to 90 or 100 points, I've seen. And keeps getting, the training keeps getting better.
There's another question, I think.
Hi, this is Kamal from Brown. I have a query. Hi.
Yes, Kamal, I can hear you.
Yeah. The delta T, is it like fixed, or I can change in training and testing?
This DT, this one?
Yes.
Yeah, this is changeable. So this varies from 0 to capital delta T. So all these autoregressive steps can be done for any points on the trajectory for any DT within 0 to capital delta T.
And that can be changed like training, testing also?
Can be changed for training and testing also?
Yes.
Yeah, yes, for sure.
Okay, thank you.
So once the training part is, we know how the training process works, we identify a representative set. So this representative set is essentially, so in the solution vector, we have temperature and species mass fraction. Instead of solving for all these scalars, we find out a representative scalar. And the representative scalars are found out such that principal component analysis on the source matrix is performed. And then we identify top few principal components. And then we identify the largest contributing source terms in those top few principal components. And corresponding species are kept. So those are the representative scalars we identify for a network. Since this combustion data set lives on low dimensional manifold, those identified representative species are kind of representable of the manifold, and rest of the species are highly correlated to the ones which we have identified and can be recovered from a simple artificial neural network. Further reduction in the dimensionality of these representative set can be done through Latin variable or using an autoencoder. And that brings us to the next framework, lattice space kinetics identification. So we use an autoencoder to bring down the dimensionality of representative set from to the latent variable space. And then in this latent variable space, we identify the kinetics through the network and then evolve in the latent space. And once we reach to the certain state, we come back to the original thermochemical case through the decoder part. So this allows us to have a first like a smaller React deponent architecture, because now the variables are the dimensionality of the input variables is small. Second, it also allows us to have a larger representative set. So the framework of React deponent is first demonstrated on a simple chemical kinetics of H2 combustion. And then we move on to the complex kinetics of endodecane, which is low temperature oxidation. And further, we demonstrate the lattice space kinetics framework on the low temperature oxidation of endodecane. So the training parameters and network hyperparameters are all shown in this table. So the training data for H2 is generated at a constant pressure reactor from Cantera for different initial conditions. And these are the initial conditions for which the dataset is generated. And these are the representative scalars which are identified out of the 11 scalars. So the network is trained on these initial conditions, and we have predictions here. So the solid line are prediction, the actual values from Cantera. The symbols are predictions from React deponent. In all the cases, we can see the predictions are in well agreement with the Cantera values. And then it is able to effectively learn the chemical kinetics corresponding to different initial conditions. In addition to that, so keep in mind, like the network is trained for these equivalence ratios and initial condition. We have tried to see the extrapolation capability of network when we go out of those ranges of equivalence ratios. So let's say for the equivalence ratio of 0.6 or 1.3, that is outside of this domain. And even for those cases, we see reasonable approximation or see good extrapolation capabilities. Occasionally, we see like it starts diverging on long when there's integrated it for longer times, but otherwise the ignition delays are well captured. We can also extrapolate with respect to the initial temperatures. So initial temperatures are these ranges, 1020 to 1200. Here we have shown results for 980 or 1240. And again, the predictions are in well agreement with Cantera values. At this point, for a smaller temperature, we can see there's a slight earlier ignition delay is observed with the DeepNet model. But again,
I have a question here, sorry. So this is Ahmed, I'm from Brown. So how did you choose the temperature range for the training data set? Because from 1000 to 1200, if you increase the range of temperature, you have different kinetics.
yes.
So have you increased the range of temperature? Because I think this is a small range.
Yeah, it is a small range. We so this, like, we wanted to see how it behaves. We could have taken a large range as well, but we haven't, like, we went out with this range only. There was no particular reason to select why we selected this range, but maybe like the transition is happening within 0.5 millisecond in corresponding to all these initial temperatures, and maybe that was the main reason, I think, and so that we can track all the parts of training. Or let's say higher initial temperatures where the transitions start happening very lower initial temperatures, the transition happens very late, and that could be a reason like we see predictions are a little off. But like, yeah, I think this was the aim. Like, we wanted to have a transition within 0.5 milliseconds.
Okay.
So Anuj, I have a question. Can you hear me?
Yeah, sure.
So in the first case, you have like out of distribution phi, and the second case out of distribution temperature. How about like if both cases are out of distribution? Did you also test that out?
Out of distribution of what?
Like, for example, like let's say if you pick phi 0.6 and temperature 1000.
Oh, okay. So I have tested those conditions as well. So it performs well for the larger temperature, initial temperatures, even though like equivalence ratio is, so one of the factor like using, one of the benefit of using paramnet is that it extrapolates well across equivalence ratio, because now the dependency in the paramnet, I did not mention this, I think in the paramnet we have one of the parameter that is equivalence ratio, and that is why we see good extrapolation across equivalence ratios, but we don't see that extrapolation well across initial temperatures. And also the extrapolates well across higher initial temperatures as compared to the lower initial temperatures. So it extrapolates well when the high initial temperatures are higher. Maybe like if you talk about, let's say 12, 40, and 0.6, it'll extrapolate well, but it doesn't extrapolate well when the initial temperatures are lower and it is out of range of equivalence ratio as well. So for the lower initial temperature, when the transition is happening very late, it has to accurately predict for longer times, and that could be a reason, I think. Maybe like it might extrapolate well when we can input initial temperature as also part of paramnet.
Okay.
I hope that answers the question. Okay. So next I talked about, we can also take a variable time stepping from the network. So here I'm showing the predictions at different time steps here in this plot. The time stepping is 8 microseconds. And in this plot we have as large as 40 microseconds. And in this plot we have a variable time step. So like it could be, so this here we select a time step based on the source terms. So this is very small when the transition is happening. And again, like in all cases, we see the predictions are quite accurate. Next, like we know the React DeepNet model is kind of projecting solution vectors in by small delta t's, but these delta t's are continuous values. So as a Jack's autograde functionality, we can find the partial derivative of our output with respect to one of the input, and that essentially is like the source terms we can get out of this network as well. We also have the ground truth values of the source term, so we can see like how well our network is trained. And here I'm showing the source terms corresponding to the normalized S2 values, and in all cases the predictions are in well agreement. Potentially we can also make a loss function out of it, but we haven't tried it. It might provide more richness to the training process, but that is yet to be seen. So next we move on to the more complex case of low temperature oxidation of endodecane. So this has very large species, dimensionality like 348 species and around 2000 reactions. And out of these many representative scalars are identified. And it is trained on these initial temperatures, these equivalence ratios and initial temperatures. And for all again, like different, so here we have predictions from React DeepNet for different initial conditions, and again for all the different initial conditions, we see that predictions are in well agreement. So for endodecane low temperature oxidation, it's very difficult for a data-driven model to capture the kinetics, because it happens at two stages. We have a low temperature oxidation, and that happens at a slow scale, and then at higher temperature, the oxidation process is very rapid or quite fast. But the React DeepNet is able to capture this, both the scales and the kinetics is properly captured by the model. And again, we can see the predictions from out of sample initial conditions. And here again, the predictions are reasonable corresponding to some initial conditions. The predictions are not that good when the initial temperature is quite, the equivalence ratio is a little off. The equivalence ratio is very low. So we see there's an early transition in happening when for a higher temperature oxidation part. And again, for when we are seeing the extrapolation with respect to initial temperatures, we see quite little discrepancies when the initial temperatures are lower. And these predictions are like for one of the largest MAs of the predictions. And so even for those cases, we see the trend is properly captured, but we don't, the ignition delay is not matching. So next we show the odd latent space framework here. The dynamic latent variables, like so the 8 dimensionality of the representative variables is condensed down to 3 variables. by using this autoencoder size. And then the kinetics is learned in the Latin space, and the predictions are done in the Latin variable as well. And again, we see that predictions are in well agreement with the actual Latin variable. And here also the one we can see the one thing to note about is that the prediction the parameters for this network are almost half than that the previous network, which were used for same kinetics, but now the predictions are being done in Latin variables, so we have a smaller network that is being used. So next we talk about the speed up corresponding to each case. For H2 case, we see a speed up of around 12.5. So it is not that huge because the mechanism is not that large, and Candera integration is it doesn't take that much or large times. However, for larger reaction mechanisms such as endodecane, we see a very large speed up of around 1500, where the Candera takes very large time to integrate for reasonable times. And the speed of kind of doubles when we are using Latin space framework, when we have a smaller React deponent architecture. So at this stage, we can integrate this framework with a CFD solver, and then so CFD solver essentially gives us the thermochemical state. Our model would be advancing that thermochemical state by some delta T, and that delta T can be arbitrarily large as long as it is within that window size and can be adaptively chosen from the CFD solver. However, there are certain requirements from the CFD solver, such as it requires to have a full set of species. Although we have a workaround to work with the subset of species when integrating with the CFD solver, but that's a different story. Next requirement is that sum of mass fraction is to be equal to the 1. So here we are starting our indices from 2 because the first scalar is temperature, and that is not present here. So the sum of mass fraction needs to be 1. And it should be equal to 1. And I just took it from loss function. So this should be equal to 1. And this elemental conservation should be there. So as reaction progresses, the elemental elements should be conserved. So let's say if we talk about here, for kth element, this is the contribution of element in that particular species, and the contribution is summed across all the species, and that total sum should be equal to some constant CK value, and it should be constant throughout the reaction process for all the elements. So we can find a mapping of left out scalar from the representative set. As I said, I mentioned that the data set lives on low dimension manifold, and then we can reconstruct it effectively, making use of just an artificial neural network. And here we are showing some results corresponding to the endodecane part. So the endodecane, the solution is evolved with the representative set, and now once we get the representative set, we can reconstruct our left out scalars as a function of the representative set, making use of this correlation net. However, this doesn't guarantee that it will satisfy those conservation laws. So for that, we can enforce the physical constraint of a species mass fraction or species mass conservation and elemental conservation in the training process of this correlation itself. So this is just the data loss we have, and then we can put additional losses corresponding to the mass fraction one. And then for the elemental conservation, summing up for all the elements. So essentially we have here the representative scalars, and then we have left out scalars, and combining both the sets, we get full solution vector. And this full solution vector enables us to put these losses in the training process. So this mapping can now be physically consistent. However, it doesn't guarantee that the solution evolved from the React deponent model will follow the conservation laws, because it is just the mapping part that is more physically consistent. So now how can we make that evolution of React deponent from evaluation of solution vector from React deponent more physically consistent? So that is where we can utilize this pre-trained correlation net in the training process of a React deponent itself. So here we have a solution vector that is input to the React component or Kinetics identifier net. We get advanced version of the solution vector. And then during the training process itself, we can get the rest of the scalars from the correlation net. So essentially, we'll have now a full set of scalars, full set of solution vector. Having access to these full set, we can now enforce these physical conservation during the training of React DeepNet model. And this framework can be easily extended to other dynamical systems also, where the dynamics is getting evolved in reduced space, but we want to enforce certain physical conservation principles or constraints. So first here we show the predictions from correlation net. So this shows that the mapping is perfect, or the predictions are agreement with what they should be. And this is here, it shows the mass conservation error. So this is error corresponding to the sum of mass fractions, and it shows that the with conservation enforced, the error have come down. Here it shows the elemental conservation error corresponding to C element. And again, with conservation or with constraint, it has come down. And for same case goes with hydrogen and O and nitrogen elements. So this is just for the mapping of left out scalars, and we can see that this mapping is physically consistent. And now here we show the predictions from React DeepNet. So here first the predictions are accurate, and then we can see that with constraint, the errors have come down for the mass conservation as well as elemental conservations also. So in conclusion, we have proposed a framework which is based on DeepNet. The approach is validated to predict for a simple fuel of hydrogen air combustion, and then a more complex fuel of endodecane. So what did we achieve? We wanted to have a reliable prediction in long time horizon, and that is kind of getting achieved through the long time prediction integration loss that we saw, that kind of takes care of, it doesn't let those predictions to diverge from the trajectory and also from the paramnet. So it keeps on informing the system about the initial states. We wanted to avoid the computationally intensive OD integration due to stiffness. And from this framework, we can take arbitrarily large time step. And this is where the most cost saving comes into the picture. And next, we wanted to advance at a variable time step, and we can pick any time step between 0 to delta t. And this is one of the requirement of a CFD solver. It enables to easily integrate it with a CFD solver. We also wanted to decrease the dimensionality of the system, and then identification of representative set enables that. And also representative set allows us to extend this approach to a large and complex fields where we have very large dimensionality of hundreds and thousands of species. We also wanted to have a physically consistent solution advancement. So that is kind of being enabled by physics constraint kinetics identification and reduced space framework. So that concludes my talk. I would like to thank my advisor, Professor Tariq Achki, my lab mate, Kevin Arslan, and Dakshaka, my funding agency, Saudi Aramco. And thank you for your attention. I can answer any questions that you have.
Thank you, Anuj, for your great presentation. So now we open the floor for questions. Are there any questions from the audience?
I have one. Anuj, hi, this is Amir from
Can you?
Brown.
Yes.
Can you hear me?
Yes, I can hear you.
Okay. So just one question. So when you tried the physical constraints, did you also try did you go further out of distribution, or did you try that?
So this part we haven't extensively explored yet. This is like a work in progress part. This was done for just methane case. So it is not even for the larger fuel mechanism of endodecane. So this is for methane with 53 species. But we are planning to extend this to a larger fuel system as well, and then for more initial conditions.
Okay. But I think the physics constraint will help you to go further out of distribution. So you should try that one.
Yeah, sure. Thank you. I will try definitely.
And And Martin will ask the second question. Martin, can you introduce yourself first?
Yes,
And
I'm
then
Martin Volksmeier from TU Darmstadt in Germany. I have a question if you might show slide 19. So, so what you show there is kind of the starting points of your trajectories. And what it shows is that you build more or less a three-dimensional manifold by the way you construct your data, right? It's a starting temperature, equivalence ratio, and then the time along the trajectories. That's your full manifold. So in this respect, is it surprising that then later when you go to your reduced scheme or on page 22 that you end up with 3 dimensions? And did you check whether this aren't exactly the 3 dimensions you put into to set up your manifold?
Can you repeat? I could not follow you properly. Sorry for that.
Your manifold, how you generate your data. You take starting points on a 2-dimensional manifold, right?
Yes.
And then you integrate them along time. That's the 3rd dimension.
Yes.
Doesn't this mean that all your data points, just the way you construct them, are on a 3-dimensional manifold by construction?
No, so actually the ODE system for a combustion is let me show some slides. So this ODE system, we have many species, like hundreds of species are there. So that is the main space we were considering, and we wanted to decrease the dimensionality of that space. So
Yes,
there's no time in that space.
I understand that, but I mean, an ODE solution is defined by the starting point, right? If you have one starting point, there's only one solution. And if all your starting points are in a 2-dimensional manifold, then your resulting points end up in a 3-dimensional manifold. Independent of course, I see that your kinetics have maybe a very high dimensional manifold, but the way you set up your data generation process, all the points end up in 3 dimensions.
Oh, okay, I see what you're just saying. Yeah, I did not see if there could be a correlation in this identification of the latent space in that reduced space and the training data generation part.
In this respect, I didn't fully understand your parameter net, but isn't this even more dangerous then? Because if you set up your space by only in these 3 dimensions, by these trajectories, and now you even put your starting conditions, as far as I understood, in your parameters, isn't there even a higher danger that you simply parameterize your trajectories? So that in the end, you don't learn the kinetics as a function of concentrations, but just as a position in your trajectories?
Maybe so there's more constraint in the network, but it helps in the sense it keeps informing the system about what the parameter is there. It doesn't let divert the solution vectors as they evolve in time. But I'm not sure if it is interfering with the dimensionality of the system.
Okay, thank you.
Thank you. Are there any questions from the audience?
I have a question following Martin. So a question on the paramnet. Do you know the method parareal that we do simultaneous parallel computation in time? It has this breakup points, and then it has a very coarse discretization that enforces similar constraints right at the breakup points, and for the same reason, to prevent divergence as you integrate out further. Is your paramnet playing the same role, if you know what I mean? Or
unfortunately, I'm not aware of that framework yet, but yeah, I hope it will be having the similar responsibility.
Okay, well, look at also your code. When you did the integration, your code is in the CFD code is in what? Is it the CFD code is in C++ or Fortran and it calls DPONet? How is it done?
So yeah, so CFD code is Converge actually, and then they have provided a UDF that is in C. So we have a API for Python which integrates this JAX code which have for this machine learning, integrates with the CFD solver. So this is how the integration is done through the Python API.
Oh, okay, yeah, okay. And my last question, can you say something again about the correlation net? I didn't follow. When do you impose this? At what stage of the, because it has to be done sort of at the inference stage, right? But are you imposing, when are you engaging the correlation net? I didn't follow that.
So correlation net, we are engaging in the training process of React DeepNet as well. So this can be pre-trained. It is just finding a correlation between our representative set and what are the left out scalars we have. Once that correlation is identified, we the weights are frozen. Now we don't change weights of this network. And now during the training part of React DeepNet, we get certain predictions from the network, but those are in reduced dimensions. So in order to find the rest of the scalars, we use this correlation net, and now we get the full solution vector. So this is during the training part of React DeepNet as well.
Okay, during the training. Okay, all right. Thank you very much. A great talk.
Thank you.
Are there any questions from the audience?
Anuj, you get you have almost 50 people attending, so that's great.
Yes.
As you see from around the world. Good topic.
Yeah. Thank you, Anuj, for joining us today. You can stay here with us because we have another speaker and another talk. So it's time to move on to our second session. Can you just stop sharing screen? Yeah.
Thank you so much for the invitation, and thank you.
You're welcome. Kazem, can you hear me?
Yes, I can hear you. Hello.
Okay, hello. Thank you for joining us today. Can you share your screen to see if there is any
Thank
problem?
you so much for the tip. So can you see my screen?
Yes, perfect. So let me introduce. Yeah.
Sure.
So now it's time to move on to the second session. Our second speaker is Kazem Meidani. He will be giving a talk on SNIP, bridging mathematical, symbolic, and numerical realms with unified pre-training. Kazem Meidani is a PhD candidate in the Department of Mechanical Engineering at Carnegie Mellon University. He joined the Mechanical and AI Lab in 2019, where he is a graduate research assistant advised by Professor Amir Barati Farimani. His research is centered around the application of deep learning for symbolic mathematics and physics discovery. With that, please join me in welcoming Kazem. And Kazem, the floor is yours. You can begin your presentation.
Thank you very much and for the opportunity to give a talk here. And good afternoon, everyone. So today I'm going to talk about my recent research with the topic of SNIP, multimodal pre-training for mathematical understanding and generation. So the topics that I'm going to cover today is first an introduction on the symbolic regression, which most of you are probably familiar with. And then I'm going to cover briefly one of our recent works, TPSR, which was published in New 2023. And then I will move to the main topic of this presentation, which is the multimodal pre-training for math, or a SNIP, which is recently published in ICLR 2024 as a spotlight. I'll talk about different downstream tasks that we can have with this pre-training model. So with this, I would like to begin my presentation with this beautiful and famous quote from Eugene Wigner. which calls mathematics an unreasonably effective tool to describe the physical phenomena and laws of physics. So in fact, any physical system, physical phenomena that we have around us can be described in different representations. One of them can be via the data observation that we can have with sensor observation on the experiments that we can get from these physical systems. And the other one is these elegant and abstract mathematical equations that can beautifully describe these physical systems. So the process of obtaining these symbolic mathematical equations from these data observations is an essential part for the scientific discovery. And these mathematical equations help us to understand these systems, build upon them, and derive more theories and equations, predict the future of these systems, and also control these systems. And they can be in different forms, such as functional relations or dynamical systems, which describe the evolution of systems in time, and partial differential equations governing different spatiotemporal systems. So what is symbolic regression in a bit of a formal way? So consider we have an unknown function f, which maps the input features x in d dimensions to a target variable y in the real space. And we have n samples observations from these systems, which can be in different conditions, like noisy or scarce observations. And we have these like numeric data sets from these physical systems. And the aim of symbolic regression is to find a mathematical expression f tilde such that f tilde of x approximates the ground truth y for every point in the training state sample. And also we want this equation, mathematical equation, to be simple such that it can be interpretable, we can understand it, and it also is generalizable to the out of distribution domain. So why symbolic regression? The next question is why we need symbolic regression, or what is important. So I want to like compare symbolic regression with a general regression framework such as neural networks. So in symbolic regression, we want to find a mathematical form for this equation f, but in neural networks, we want to optimize the parameters theta in the neural network that can learn this mapping from the x to y. But in comparison, the neural networks are difficult to interpret. It's very difficult to see what are they like showing to us. But when we have a symbolic expression, it is first interpretable, meaning that when we have this form of equation, we can see how these like features are combining to each other and build the target value. And more like above that, it's generalizable, meaning that we can greatly describe the outside of the distribution of the training. And also in this plot from Barker et al., it shows qualitatively what are the advantages of the symbolic regression in comparison to deep learning. So we can see symbolic regression in one hand, deep learning on the other hand, and distributed approaches in the middle ground. So we can see that the main advantages of symbolic regression are in their interpretability of the results and generalization, which is very important in the domains of physics. But on the other hand, for the deep learning, we have better performance in more complicated, high-dimensional problems, and also they are better in the expressivity of the model for different tasks. So,
Kazem, sorry, can I interrupt?
Sure.
Yeah, this is Zoran from Brown. So could you go back to your previous slide? Actually, this slide, but previous figure.
It's fine.
Yeah. For the figure on the right, could you elaborate? What are they like? Such as the dots are the data, right? The dashed line. What are the other lines?
Sure. I will describe it. So I had it right now for as the like general figure, but I'm going to like explain it more like what each of them talk about. So, but like if I want to like mention, so the dot points are training distribution here, and the other curves. So the dashed curve is actually the ground truth data. The green curve is the curve that was obtained with MLP or and also like other shallow methods. So they cannot go out of distribution. But the red curve is a symbolic regression method from the search methods. And the orange curve is actually our method that can like find the equation. So once we find the equation, we can generalize the out of distribution. That's the message that this figure wants to convey. That the symbolic regression helps us to have a generalizable like model.
Great. Thank you.
Sure. So yeah, now that we discussed why symbolic regression is important and why we need it, we want to talk about the challenges of symbolic regression. So why is it difficult? Why can't we just do it? So in comparison again with the neural networks regression, there we want to find is optimal value of parameters theta, and we can write the loss and the whole network in a differentiable way and use gradient descent to update the values and find the optimal value of theta. But in symbolic regression, we actually want to search in a non-differentiable, usually non-differentiable, and very large search space of the class of functions. We show it here as capital F that contains different discrete functions that we have. So in fact, the space of possible functions that we can have is a combinatorial search space, which is very large. So why combinatorial? Discrete part is from the different types of skeletons and forms of equations we can have. And on top of that, we have different continuous values for the constants and coefficients. So it's a super large space, and we need to search one by one in this space to find an equation that fits the data well or have a lower loss value. So on top of this, I talked about the very large search space and talked about the coefficient of dominant terms. So on the plot on the right top shows, it's a plot from Laplanche-Short in 2020. It shows that with fair assumptions of the complexity of the model, the internal nodes that we can have for the expression tree, the number of possible expressions, just the skeletons, goes too high, and it's almost impossible to do exhaustive search in this space. And on the plot on the right bottom shows that you can see this is the sine of 10x plus x, and the other one is sine of x plus 10x. So these two equations actually have the same skeleton, and only difference is that the value of coefficients are exchanged in these two forms. And you can see that even though they have the similar symbolic form, they have a very different numeric behavior. So there's a disparity between the symbolic forms of equation and the numeric data sets. And the last challenge also can be new input data, which especially in the applications of dynamical systems or PDs, we can have a scarce, noisy data or irregularly sampled data. So there have been lots of efforts in SR community and literature to alleviate some of these challenges and move towards solving some of these
Kazem, can I ask something? What happens if when you have multiplicity of solutions like in nonlinear equations, simple events? So multiplicity of solutions. Beyond regression, let's say we do solving PDs.
Mm-hmm. So you mean if you have same equation but different solutions, right?
Right, and there are solutions which are legitimate, but there are also solutions which are unstable, but solutions which are stable, but multiple solutions. Many nonlinear ODs or PDs will have multiple solutions.
Okay, sure. So this the most of my efforts are being in the functional symbolic regression, means that it's not OD or PD, but we have the similar theme here, that we can have not only similar symbolic forms that have different numeric behaviors, but also similar numeric behaviors that have different symbolic equations. And one of the goals of SNIP that I'm going to talk about is that we can learn a joint embedding from these two different spaces of the numeric behavioral solutions and the symbolic equations. So we can kind of learn a mapping between if we have this symbolic equation and with different coefficients or different let's say in ODEs can be different initial conditions, for example. If we have different solutions with different numeric behaviors for it, it can learn that they are all kind of similar to each other. But I would say this is a very important and challenging aspect that it really needs more investigation in the future, because in terms of natural language or other fields, usually we have this correspondence in some sense, but in mathematics it's more complicated. Okay.
Thank you.
Sure. So I will continue on the methods that we can try to address some of the SR challenges. So there have been lots of efforts in the SR literature, and I've also done some works during my PhD. So there are some different ways to try to either reduce the problem to a simpler problem or try different approaches to solve this SR with different perspectives. So one of the first ones is to use linear models with nonlinear bases, meaning that we simplify the problem. The second one is the deep learning plus search, meaning that we want to have a learning for the SR with viewing the mathematics as a language. And the last one, which is the main focus of this presentation I'm going to talk about, is to use symbolic numeric pre-training model to have a joint like representation from both of them. So the first approach, which is like actually similar to the concept of SINDI, is to reduce and simplify the problem in such a way that it can be solved in a differentiable way or with just linear regression model. So the assumptions of these linear models with nonlinear bases is that we assume that the function admits a representation from a predefined library that we can like define ourselves, and then we reduce the problem into actually a linear regression with nonlinear bases. And we also assume that the function f is simple, meaning that it has takes a sparse representation from this library, and we just solve a sparse linear regression problem with different like solution techniques. But the problem is that this assumption is too restrictive in many applications, specifically in general functional symbolic regression, because like let's think about these two examples of equations. We simply cannot have every possible term of sine of C2x in the right-hand side in the library, because it's the coefficient value that we want to like consider. There are some tricks to alleviate this issue, but still this like issue exists. So what is the better way to have a like flexible representation for these like equations is the actually expression trees. So we can see that we can describe each of these mathematical equations with an expression tree where the nodes actually are binary nodes or unary nodes, and the leaves are the either constants, coefficients, or the variables. You can see here, for example, it is 0.1x plus sine of x. You can represent this in this way. And there is this like very helpful correspondence between if we just do the pre-order traversal of these trees and write it in the prefix notation, there is almost one-to-one correspondence between these like expression trees or equations and their sequence written in a prefix notation. That helps us a lot to search now in this space. This is like flexible and don't have that like restrictions of linear models. So what are the methods that we can try to find an equation here now? So the first approach, the traditional methods for SR are search methods, meaning that we have these, as we discussed, we have these like large combinatorial space, but we don't want to do exhaustive search one by one. What we can do is that at least have some intelligent search via gradient-free optimization methods or reinforcement learning. So with gradient-free optimization, for example, genetic algorithms are very famous in this field. We can have different tweaks and changes in the discrete space of equations. For example, we can do mutation or crossover and get new populations of equations with the hope that these new equations have a better fitting on the data. But there are some problems with this. The first problem is that for each new data set and for each new observations, we need to do this search from scratch from the beginning. And this is a large combinatorial space, so this is very computationally inefficient to do this. And above that, another very important challenge is that there's a disparity of symbolic and numeric representation that we discussed. And this causes that this search actually can be not very meaningful. So let's say that we do some mutation and change one operator of like addition to multiplication. It can change the behavior of numeric behavior that said very much, and that's like that means that actually we don't have a real meaning of approximations of gradients in this search. We are just doing something a little better than exhaustive search. So the other view, the other perspective to solve SR, which is most recent, is to do learning instead of search. So in this perspective, we see mathematics as a language. So similar to how we can caption an image like this, like an apple is falling from a tree, we can like look at it, look at math as a language of nature and see that, okay, we want to like somehow caption this. So here I just showed like an example of again PDEs, but as I said, my works are mainly in the functional symbolic regression methods. But we can do autoregressive token by token generation of the symbolic mathematics like operators or the constants and variables to generate the like scientific caption equation for the observations in some sense. So the way that we can do it, and thanks to transformers, and that they are very helpful in seq-to-seq models, is that we want to learn this mapping now from the mathematical numeric data sets to the equations. So let's say that we have a large data sets of data sets. So each of these data sets is a numerical data set, and we have contains n observations in d features and one target variable. We want to learn an encoder decoder transformer, and we also have the ground truth for the equations. We talked about how we can generate it, but let's assume that we have a large number of these pairs of equations and their numeric data sets. And then we can use, similar to language models, a token level cross entropy loss to generate the tokens and match it with the ground truth. So what is the advantage over the search method is that now that we have a strong prior knowledge, because we have these like pre-trained like phase, we can leverage these like patterns that are learned in prior. And for that, we can have a fast inference time. In a single forward pass, we can give the numeric data as the input and get the equation as the output. And they're having different ways to do it. One way is to do a skeleton base, meaning that we first predict the skeleton of the equation and then optimize the constants with some other optimizers like BFGS in an end-to-end manner, meaning that we predict the full expression, including the constant, and then just refine the constants. But this is not the complete solution. There are lots of challenges, again, with the learning methods. So although there exist lots of challenges so far, here are three of them that we have tried to address. So the first challenge is about how to handle this numeric input in language models. So we know that the language models are good with the natural language or even in code generation with the codes. But how can we handle the numbers and also numeric data sets in these transformer models? So for this, we rely on work from Shard 2022, and there are like every day more researches in this field, because it's very important also for the natural language processing field. So we have this duality and the balance between the scale and the precision. So let's say that we have both values of 10 to the power of -2, which is a very small value, and 10 to the power of positive 34, which is a very huge value. And we have both of them in the same data set. So how can we handle that such that we don't wash out any of these two? We don't do the outlier removal, we don't do wash out of the small values. And also the precision. So how precise we want these numbers to be. So for our work, we rely on this a specific type of number tokenizations. So in the vocabulary of language models, we need to have finite value of tokens in the vocabulary. So, but the numbers are infinite. They have a continuous form to get for the numbers. So the one way to do it is to tokenize each number in 3 tokens. First is the sign, positive, negative. The second one is mantissa, which can be the first 4 main significant digits. And the third one is the exponent, or the scale of the value. So the next challenge is that generative models hallucinate, as we know that also in the language models. So how can we solve it? What with this hallucination, I mean that, so we trained our learning model, the transformer, with this objective of the token level matching objective, meaning that we have, let's say we have this ground truth sequence, and we want to predict the tokens one by one. And what we tell the model is to try to generate the next token to be the same as the ground truth token. And it's like teacher forcing. So what's the problem here is that it has a mismatch with the objective of SR. In traditional SR, the objective was actually to fit the data well. But here we don't see any of that objective. So we need not only to match the language, but we also need the model to describe the data well. So to solve this issue, they're having different ways to fine-tune language models for different secondary objectives. So 2 methods that are common are first alignment, and the other one is planning. So alignment is actually what ChatGPT, for example, does. It's based on reinforcement learning from human feedback. So we have the model pre-trained on something, and we have some instruction or reward model, and we tell the model that, okay, try to not only have that previous knowledge that you have, don't forget that, but also try to be fine-tuned based on the secondary object that I want. So the other way to do it is planning that we did in our method in TPSR. So the idea is that in the decoder stage, we can have a RL platform like Monte Carlo tree search that generates the next token not only based on the transformer prior knowledge, but also has a look ahead and see what's the fitting of the equation and tries to generate better equations. And I'm going to into details of this work because I want to move to the main topic, which is the SNIP. So this third challenge is a discrepancy of representations, as we discussed. And one way to alleviate this is with multimodal pre-training. So the motivation behind this work is that we see these physical systems, and previously what we mentioned is how to go from these numeric data sets to the symbolic mathematics, just symbolic regression. But if we have if we look back and have a broader view, we can see the numeric data observations and the symbolic expressions as two different representations from the same concept, from the same physical system. So this has some analogy with how images and language actually describe the same thing. So if we look at this image on the left, for example, we can see a young boy playing basketball. And if I ask you just by seeing this image, think about some caption for it, you can easily think about it. And if I ask you to just read this caption, a young boy is playing basketball, and imagine some visual concept or image for it, you can again do the same thing. But let me ask you if you can just see the numeric data observations, is it easy to just imagine some equation for it? Or if you just see the equation, is it easy to imagine how is the numeric behavior for it? So it's challenging, but it's again, there is this analogy between these two representations. And there have been a lot of works recently in vision language pre-training and learning a joint representation for the vision and language. One of the groundbreaking works was CLIP, contrastive language image pre-training, where we have a large pre-training phase of the corresponding images and their captions. And with the contrastive laws, we learn a good representation, which can be very good in zero-shot classification and prediction. So inspired by these successes in the language vision, we proposed a SNIP, which is symbolic numeric integrated pre-training. So let's consider that we have a large batch of symbolic expressions. Here I showed 1D, but in our case, a SNIP can get to up to 10-dimensional equations. But let's say that we have a large batch of symbolic expressions and their corresponding numeric data observations in a tabular data. So we first need to embed and tokenize these, each of these modalities, then pass it to the symbolic encoder and numeric encoder, which both of them here are transformer encoders. After this, we need to pass it through an attention pooling phase that actually pulls over the sequence length such that we get one vector representation. Here is of size 512 for each equation and one vector representation for each numeric data set. And at the end, we can use a contrastive loss, which the whole objective of contrastive loss is that pull together the matching pairs of the symbolic equation and the numeric data set and repel those non-matching pairs. And we did this jointly pre-training on over 50 million paired examples, which were generated synthetically. So here is just shows a simple scheme of how contrastive loss works. So let's say we have different equations in symbolic form and their numeric corresponding data sets. And this is what a SNIP contrastive loss does. Pull together those matching pairs and repel those non-matching pairs in the latent space. So I will first talk about the architecture and the data generation and then show the results of it. So for the pre-training data generation, this is one of the main aspects of a SNIP. So we actually, we need to generate both the symbolic form, the sequence, and the numeric data sets. And for the expression generation, we actually rely on the previous work, again, from Charton, which like in general, it first samples not different number of binary operators and unary operators and makes this placeholder for the expression tree, and then fills this tree with a predefined vocabulary of unary operators, binary operators, variables, and like constants. And then with this, from this, we can get first with the periodic traversal, we can get a sequence of the equation like this. So this is a sequence. And also we can calculate the values of x and y on a set of like acceptable range and get this numeric data set. So this is very important that we have this very simple and fast way to generate the data in a very large amount of data. So the first part of the architecture is the symbolic encoder. So as we said, we have this infix equation. Let's say here x squared cosine of 0.5x. We first write it down as a prefix equation, and then we need to tokenize it to different tokens in the language model. And because this order is important in the sequence of equation, we do first this positional encoding, then pass it through several layers of transformer encoder. The output of this encoder will be bite-sized by the sequence length by the embedding dimension, and we do this global attention pooling to map it to the embedding dimension. Similar happens with the numeric head. The only difference is that the order is not important in the numeric data. So if you just change the pair of x and y, it doesn't matter. So we use actually kind of set transformer, in that we don't force the position embedding for this model. We have all the numbers as we discussed in a specific tokenization method. And then we use the feedforward network to embed it. And again, this similar architecture is used for the numeric encoder and the global attention pooling, and we get these vector representations. So now that we have these vector representations and we use that contrastive loss, we want to examine what is the representations after the pre-training phase. So here I show the a 2D TSNE plot from the latent embeddings from the symbolic head. So which means that I give different equations, symbolic forms of equations only into the symbolic encoder. And the color of this TSNE is based on the numeric property, which is here a convexity of the equations. And also I've annotated some of these points to their corresponding numeric data behavior. And we can see that actually in the latent space, we can see it is structured with the numeric behavior of these data sets, but it only has seen the symbolic equation as the input. So this is very qualitative analysis, but for the more rigorous evaluation of a SNIP, we did two different downstream tasks. The first one is cross-modal property prediction. With this, I mean that we want to predict numeric properties from symbolic input and the other way around, symbolic properties from the numeric input. So here I've shown two examples. There are more examples in the paper if you want to check. So example that I've shown here is first non-convexity ratio. This numeric property describes how convex or non-convex is the mathematical data set in one-dimensional. So if it's fully convex, the value is 0. If it's fully non-convex, value is 1. And for others, it gets something in between. And also upwardness or downwardness of the function, meaning that if it's monotonically increasing, gets value of 1. And then decreasing, gets value of -1. And for others, it's something between. So we want to predict this numeric property by only seeing the symbolic equation as a form. And to compare and evaluate the SNIP, we have three different variants for the encoder. The first variant is an encoder which is initialized from random weights. The second one is initialized with the SNIP pre-trained weights, but the weights are let be frozen. And the third variant is that we have the SNIP encoder, but let it fine-tune. And for each of these cases, we have a predictor head, which is a simple two-layer MLP that tries to map, do a regression task to these labels of non-convex ratio and upward downwardness. So
hello.
Hello.
It's interesting. So this is Lulu from Yale. So I have one question here. So I'm just wondering, so why do we need use this prediction to predict the property of properties of the symbolic. For example, I can do some simple calculation to compute all of these. Probably its computation cost is even less than a forward pass of the transformer.
Yes, so you're correct. So I mean, for these cases of like for like non-convexity ratio, if you have a 1D equation, you can do just like 2 times derivative and see if it's convex or non-convex. So this is actually I would say a toy experiment that shows that this model is capable of understanding the other like modality. So the goal is not like to this. It's not like the main novelty of the work is not just to like predict this property. Of course, we can do like upward downwardness with either from the symbolic equations or even with the numeric like calculations to see if it's a convex or non-convex. So actually we calculated the ground truth values with the same way. So we had these like easy ways to calculate the ground truth. So that's not the like main contribution. The contribution is that we want to see if the model with just like without these like additional information, additional like ways to calculate, can it understand the other modality by just seeing the equation or not?
I see. Oh, thank you. Another question. So in your data set, you only plot 1D case. So have you also have the high dimension data in your data set for training and testing?
So we have like 2 variants of SNIP. One of them is for 1-dimensional and one of them is up to 10-dimensional. So So we can consider up to 10 dimensions. Specifically, I will talk about it in the symbolic regression test. So again, there is this limitation of the like 10 dimensions. We don't go higher than 10 dimensions because if we don't see it in the training distribution, we cannot expect the model to generalize to more than 10 dimensions. And one of the main limitations is the maximum length of the equation that we can consider in the training distribution. So if we can go to the higher than 10 dimensions, we'll have longer and longer equations. But we have some like limitation for the length of the equation that we can see the sequence in the language model, because the transformer complexity is like very like correlates with the length of these equations.
Okay, thank you.
Sure. So yeah, so for the property prediction task, we want to like compare these 3 variants with all of them trained fine-tuned with the predictor head with the regressor. So plot on the right, the x-axis shows the number of training samples. So number of labeled samples. So this is after pre-training, if we consider it. Number of labeled samples that we have for a specific task of non-convexity ratio prediction. And we can see that even with only 100 labeled samples, only 100 equations with their non-convexity ratio, if we do it with the supervised manner without the SNIP weights, it's not doing well for the R-squared. But if we use the SNIP like frozen weights, as we also saw in the embedding representations, we can get a very better performance. And we can see that when we increase the number of training samples, like around 1 million, the supervised model tries to catch up and get better, but it's completely expected. So the main power of a SNIP in this task is that if I wanted this, I have a desired property that I care about, I can just adeptly fine-tune the SNIP with very low number of samples. It's like a few shots learning, such that the model can learn very good and can do the very good regression task here, or even classification task. You can see here also the numeric, the quantitative results of the R-squared and MSE for the supervised compared to the SNIP. You can see that both of the variants of SNIP are much better, but with fine-tuning, it gets also even a little better. So as I said, more of these properties, both symbolic and numeric properties, are in the paper. And here also I want to show a qualitative result for these comparisons. So each of the rows shows one of these tasks. The higher row shows the non-convexity ratio task, and the lower row is about upwardness. And the column on the left shows the supervised model without the SNIP weights. The second column shows the SNIP with the frozen weights, and on the right we have the SNIP with the fine-tuned weights. So you can see that, for example, for the non-convexity ratio, where we don't have the SNIP weights from beforehand, it doesn't get that much structures of the this property. It kind of overfits and doesn't perform well. But when we have the SNIP frozen weights, you can see that this is this just sees the symbolic equation as the input, but you can see that it is structured by this numeric property. And when we do this fine tuning, even for a few like iterations, we can see that even it changes to a more linear like pattern of the like values based on that specific property. You can see that it like based on the properties that we like fine tune for it, it gets a very like linearized pattern. So the second downstream task is to use a SNIP for symbolic regression. So in a SNIP, we have two different encoders, and we don't have any decoder head that can generate equations for us. So to do that, one way is to train a decoder head on top of the numeric a SNIP encoder. So we have the SNIP encoder numeric head, and then we can use a pre-trained E2E decoders from a previous work and learn some mapping layers, which are mostly some MLP layers that map the dimensionality of the length and space to the input of the decoder and generate the equation. But the experiments show that this is not enough, because this is, after all, a learning, again, from numeric input to the output. It doesn't see the like performance of the like fitting and other things. So how can we use this meaningful representation in the latent space? So this is my like favorite plot from the SNIP. So this like shows a scheme of the latent space from a SNIP. So I'll try to explain this like plot. So if you consider each of these points represent a point in the latent space that is encoded with the numeric encoder from these like numeric behaviors. So let's say we have this numeric behavior as the blue curve. We encode it and we get this blue point. Also, we have different set of destination points. Let's say this orange curve, and we get encoded and we get this orange point in the latent space. If we do the interpolation here, so let's say this is Z1 and this is Z2, and we do Z1 plus Z2 over 2, and we get this black point, and we decode it now and find the F, compute the F, is a non-differentiable way, compute the F on the X and get the Y hat, and we plot it back. And we can see that for different like pairs of source and destination, the behavior of the like computed in black point is actually semantically in between the source and the destination. So it can get shifted, or the different slopes, or like different even like behaviors. So this means that a SNIP latent space is not only low dimensional and continuous, but it's also interpolatable. So this is what we want to like exploit and use. So now that we have this continuous, low dimensional, interpolatable, and more importantly, it's both numeric informed and symbolic informed, compared to the previous case that we had different types of equations. It's a like large discrete and combinatorial space, and it was also, as we saw, numeric ignorant. So now that we have this space, we try to search now in this space instead of that like discrete large such a space. So what we do is to first augment a population from the SNIP. So for the augmentation, we can do adding noise into the input or into the like latent embedding, also do some subsamplings from different parts of the numeric data set. And we have a first initialization for the population. Then we can, for each of these points, we can pass it to the decoder, generate an equation, do the constant refinements, and then it's a non-differentiable part that we need to calculate the F on the X to get the Y hat. Then we compute the R squared of the Y and Y hat as a reward. And we use that reward to update the population over and over until we like pass one of these like criteria of the stop. Like either we get a high and good accuracy, or either like we pass the maximum iteration that we have. So it's still optimization of like non-differentiable gradient-free optimization, but the space that we try to optimize is much better than the previous case. So for the results and the like experiments, we evaluate the SNIP on SR bench, which is the benchmark commonly used in symbolic regression, which includes 3 different types of data sets. One is Feynman equations. They're like mostly like basic physics equations like this, 14 equations of ODE surrogates, And there's another part is 57 data sets of black box, which we don't have the underlying equation for them. And the fourth part is actually an in-domain state data sets that we compute from the same distribution of the training, but like new equation generated with different C. And for the metrics, the main metrics of evaluation for symbolic regression is first the fitness, like how the equation fits the data well. For that, we can use R². And the other one is the main one is complexity. So the lower complexity or the simpler the equation is, the better for us, because we can have better interpretability for that. So here it shows like Pareto plots of the rankings of the complexity and the accuracy for a SNP and different algorithms that are available in the SR bench. So most of these other algorithms are based on the genetic programming and traditional search methods. For black box, it also includes some of the shallow machine learning methods. And so because both of them, the y-axis is complexity rank and the x-axis is the accuracy rank, the lower is the better. So we need to focus on the Pareto front. And we can see that a SNP is on Pareto front for all these three types of data sets. So we can't say that like a SNP is always the better for all the cases, but it has a competitive performance with the like state of the art. And the most important part is that it's a new way to look at the problem compared to the like traditional ways. And here it shows a general, like very like general view of how a SNP works. So the main point of a SNP is that it's not only learning based and it's not only search based. It's a learning plus search based. So we have a learning. We use the prior knowledge of the like encoder decoder transformers and its frozen weight and also the decoder part. But we also do the search part. So the difference is that we don't do the search from scratch. We have a good initial point to start with, and then we do the search from that point. Here in the table below shows that if we don't do the LSO, which is latent space optimization, performance of a SNP is not that good. Actually, we need this search part on top of the learning such that we get the better like performance. And you can see that this is like just a scheme of like how the population of agents like can like iteratively updated in this like continuous space. So that was for the SNP and for the limitations and the future of the work. So one of the main limitations of the current like framework of a SNP is about the data. So in traditional search methods, we are flexible on how to evolve our equation. But here we have a learning base, and that means that we are somehow bound to the training distribution that we saw in the like pre-training phase. So for example, we cannot expect the model to generate longer equations that it has seen in the training distribution. Or if we have specific cases like x to the power of x to the power of x to the power of 2, which hasn't seen in the training distribution, we cannot expect the model to like learn and generate that for us. Again, we have this maximum length for the like sequence input and the maximum dimensionality that I discussed is 10 here. Also, equation vocabulary. This is also the same. It's true for traditional SR methods that we need to define our vocabulary. The more terms that we consider, it's more challenging to learn, but it is more general. And it's really interesting to see how we can like extend this work to like ODEs or PDEs. And the last part, which I think is like a challenge in SR community, is about the benchmarks and the evaluation metrics. So far, in terms of both benchmark data set that we evaluate and also the evaluation metrics that we have, there are some like problems and we can do better than this. And for the future, and I would like to really like to emphasize that we did these two downstream tasks for a SNP, but I believe that a SNP is capable of more different tasks that we can do. So because we have this shared embedding of the symbolic and the numeric part, we can do different tasks such as symbolic to symbolic, such as symbolic integration or symbolic solution, or symbolic to numeric, solving or finding the values of the equation, numeric to symbolic as SR, or numeric to numeric, such as zero-shot forecasting. So there are like more applications that we can use a SNP for. And with this, I would like to thank you again for listening to my talk. Here are the QR codes for the SNP paper open review, and we also have released the models and the codes on GitHub. Please feel free to take a look. Thank you so much for listening.
Thank you so much, Kazem, for your great talk. Are there any questions from the audience for the speaker?
Couple questions.
Yeah, Tom, can you
Yep.
introduce yourself first and then ask a question?
Hi, I'm Tom Bertlin. I'm a research software engineer at UMass Lowell. So I have one very quickly. How big are these networks? These hundreds of thousands of parameters for your
How
problems?
big? Yeah. Our SNP model is around 40 million parameters. It's trained on over 50 million parameters, actually. And yeah, I mean, it was quite, the pre-training phase training was quite long because we had academic resources with 48 GB. Like the last model that we trained for 10D was almost 3 weeks training.
Okay, this is also my next question. I mean, how long? I guess that's the pre-training part. How long does the latent-based optimization part take?
Great.
So you can do online?
Yeah, so actually latency optimization is, so we had the previous work TPSR, which is the decoding stage, and this is latency optimization. So the main bottleneck of latency optimization, so we have the whole model trained, so we don't do any training there. You just need to sample points in the latent space and then decode it back, get a generation, get the equation and compute it. And the main bottleneck here is to how to decode this. So it depends actually on our choice of how big one we want the population to be. So we want only 20 or 100, how many population we want to have. And also if we want to, how many there's beam search and sampling, what is the beam search size for our case. But actually I had, I can share my screen. I had it. So yeah, can you see here comparing the time of the SNP for others? So we actually show that, so the SNP time is somewhere in between the times of the traditional SR methods and the very fast single forward pass. So in single forward pass, we get almost 1 second for generation. If we have a traditional SR method, if the equation is complicated, it can go very long, even 24 hours or something. But for a SNP, it's somewhere in between. It's almost in minutes, I would say.
Hey, one more question. What about vocabulary expansion online? If you can somehow see that you need there's a hole in your vocabulary where you need to add something.
Oh, okay. So I think that's not possible right now, because if you want to change the vocabulary, you need to do the training phase. I think this is also true for the language model. So it's not easy. At least you need to do the fine-tuning part, so to cover new samples, lots of new samples with this new vocabulary, new parameters in the vocabulary, such that the model can adapt to this new vocabulary. So it's similar to language models. If you find a new word and you want to consider this in the GPT model, it's not, I think it's not very easy to do it.
Is there work on that people are trying?
I'm not very familiar with this. Maybe, I'm sure there is, but I'm not very familiar with this.
Okay, thank you very much.
Sure.
Are there any other questions?
Maybe Raj has questions.
Also, I have a question. I look at your code on GitHub, and I saw everything is written in NumPy, using the NumPy library. But as PySR is using Julia backend, and it is very fast in comparison, to GPLearn, I think for having a faster methods, you can at least rewrite a part of the code in Julia or something like that.
Thanks for the comment. I mean, for the learning part, for the SNIP and the TPSR, because we have the learning, it's actually
Yes.
PyTorch. So we need to have this whole model of a transformer, the PyTorch. And the only part that we do the search is in the decode again and iterate it. So we actually not searching in the discrete space. So that's why I think it's not very straightforward to do this in Julia, and we need to it's much easier to do it in Python because we already have the whole model in PyTorch, and we
Yes.
need to have this decoding in to get the new equations and the outputs. So PySer actually is based on genetic programming methods. So there we have these lots of different searches. That's very important to be very fast. And so that's why it can get benefits from a very fast platform like Julia. Yeah.
Hey, Kazem, this is Raj from Brown. I just had a couple of questions. So how do you define the complexity a priori, for symbolic regression, when you prepare it? Because what I have observed, when you have a noise in the data, complexity for a vanilla symbolic regression, if we are not using SNIP, complexity becomes very high. So do you have any comment on that?
Sure. So complexity is not defined in the priori for the training distribution. So because for the training, we just care about the equation and the matching numeric data. So we have a specific type of expression that's generated, and we have a numeric part. But complexity is important for the evaluation. When we generate an equation, we want to see how complex it is. So the way we try to reduce the complexity is to add an additional part to the reward model. So the reward model usually consists of two parts: higher fitness accuracy, or higher R-squared, which is corresponding to the lower NMSE, and the lower complexity. And for our case, the complexity is defined as the length of the prefix notation of the equation. So if there are two cases, so here you can see in this short video that when we have equations that are longer, we have more complexity, and we have this additional penalty that we the less complexity is more favorite. So we have a balance. It's regularization. We have one part which is a higher fitting accuracy plus lambda, one part which is lower complexity. So we try to, if there are two different equations that have the almost same performance, we favor toward the model that has less complexity, if that answers your question.
Yes. Yeah, because when complexity is high, it basically overfits actually for testing data sets for vanilla SR model.
Exactly.
But if you go to vanilla SR model with the noisy data, you always get the very high complexity if you go for the clean data. So that was kind of a riddle how to choose you can stop the regression on the basis of thresholding the complexity, but it may have the underfitting nature for that. Yeah.
Exactly. Yeah. There is a balance. Yeah, I completely agree with your point that there is this balance always, especially when we have noise. One problem is that it's kind of difficult to know if it should be washed out, or is it some participating form. So because we have always these dominant terms in especially physics phenomena, so we don't it's kind of difficult to assume if we need to consider this additional part or not. But this is very similar, as you said, to the underfitting and overfitting that we have in the black box neural networks models. We also have the same thing in symbolic regression, and we don't have the results here, but there are some plots and figures in our TPSR work that shows that if you have lower of these complexity regularization, we get higher longer equations. And for longer equations, it's very interesting that it fits better in the training set, but fits worse in the testing part and generalization.
Yes. Yeah. Thank you. Very excellent talk. Thank you very much.
Thank you so much.
Kazem,
I have.
can I ask a question? Which is a question that Raj likes. Who just asked you the question? He likes PySR.
Yeah.
But I saw a reference, but you didn't do any comparison with PySR.
So the time that we are working on it, so there's this SR benchmark that we have, and so it's like people have like different algorithms combined into this SR bench. And it's really usual to like compare with this. So PySR is like last year or something. So it wasn't like at the time that we were doing this comparison, it wasn't included in this SR benchmark. So I'm not sure with where like PySR appears, but the best SR methods right now are like Operon and GP Gomea. So you can see that they even like some of them, they even have better like accuracy than SNIP. So I'm not sure if like PySR is better than them, but I don't think that. But I assume that this is like in this almost the same place. But as I said, I also like know like Professor Miles Cranmer, so he's actually in my like PhD committee. So I talked a lot to Miles, and the main like point of SNIP in our work is that we have like a new perspective, a new future for the learning plus search. The PySR is an optimized way to do the genetic programming for segregation, I would say.
So Raj, where do you think, where does this PySR would be where for this problem? It looks to me a simple problem.
Yeah, so I'm not familiar with Operon and GP Omega, the Gomea, but I can tell that PySR has a little bit different algorithm than a pure genetic evolutionary algorithm, because in typical genetic algorithm you have only one island of the population, and here you have a multiple island of the population, and you the mutate across them. So that is kind of some improvement which does a very fast job for the symbolic regression. But I'm not sure about underlying algorithm for these two packages, but it will be worth looking for these two. So
I think PySR, the last time I saw the SR benchmark, PySR was was in the pending process of combining with SR bench. So I'm not sure if it is right now combined or not, but it's a really interesting thing to see and like find the position of PySR in this plot.
Yeah, I think they combined up to a certain extent. Last year, they showed some benchmark in the PCTS workshop at Princeton. So I think that will be, you can check that. I think they have some certain benchmarks now available.
Sure.
But Zhenjiang or Zogren have used Operon. I see that Zogren put the URLs on the chat, but have you used
the two links? No. So I just checked the SR bench website. It was updated 2 years ago, so maybe they didn't have pure SR back then, but it's a pretty old website for symbolic regression bench. I'll put in the chat. But
sorry,
no,
Nazan,
we haven't used it.
I interrupted you. Nazan will have the last question.
Oh, I wanted to ask how like sensitive is your method to parameters value in your method? I mean, how difficult is tuning parameters in your method? Does it change the result a lot, but or it is not very sensitive to the value of parameters?
By parameters, do you mean the model weights or do you mean coefficients in the equation?
I'm not sure that what are your input parameters to use this method to like approximate the analytic expression of the curve or whatever you have from the data, but I am like asking a general question. Yeah,
parameters or values? Nazanin, parameters or values? I think you're thinking about not inputs.
Yeah, I am thinking about PySR because you have to set the complexity number, like the number of populations, the number of iterations, and yeah, can you answer this question like based on your method?
So one like difference actually I should have included here. So one of the like I would say advantages of these learning methods over assessment methods is that they are not that sensitive to hyperparameters. They are limited to train distribution, but they don't have that much hyperparameter to change. So parameters to the hyperparameters that we have for the search methods, actually we need to actually tune it, as you said, for example, for the like different optimization methods. For our work, we have actually a network, a neural network that gets the input as a numeric data and generates the equation as the output. So this whole network is like trained based on the backpropagation to generate the data better. So in the test set, if it's like complete only like learning method, we actually don't have any parameter to tune. We just put the numeric data as the input and we get the equation. If we do the learning plus search, similar to the TPSR and SNIP, the only parameter that we need to like change for TPSR is only this like complexity regularization, where if you see our TPSR work, we have this sweet spot for the value of lambda. And for a SNIP, the parameters that we have is the number of population size only and the stopping criteria. And I don't have the results for that right now, but I think we have some like results in the supplementary figures.
Yeah. I wanted you to mention that part because you have a pre-training process, so it makes it easier for the user. Because in comparison to other like symbolic regression or methods, you have to tune all the parameters. Are there any other questions from the audience?
Hi, can I ask a question here? So this is Panos Tinis from Pacific Northwest National Lab. In one of the first slides, you said that symbolic regression is more interpretable, but also more generalizable compared to, let's say, neural networks. And I understand the argument about being more interpretable, but I don't understand why it is necessarily it has better generalization properties.
Sure. So the reason is that we find a mathematical equation that governs the like data. If we have like if we assume that we have the some closed form for the like phenomena or the system, which is the main assumption of the symbolic regression. If we find an equation, this is the like general universal equation that like can describe the system in any place of that system has. It doesn't care about like where we sampled the system for. For example, I would say like a very simple example is that if we only see an apple falling from a tree and we can like capture these like videos of like apple falling from a tree, and we can train a neural network for it that can learn the position of apple in 1 by 1, and it can also generate like videos of apple like falling from a tree. But it's not generalizable that we use this like neural network to give us some sense of how can we like land a like rover on the Mars or something. But if you find the equation, like the gravitational equation of the like apple falling from a tree, that's a universal like math equation that governs, and it can be applied to different applications. And really, that was like very general.
But this assumes, excuse me, this assumes that you have found the correct equation.
Of course.
So that's my question. How do you know that the the equation that you found is the correct one? Because the way that you find this equation is based on certain data, and that data could be a small part of the phenomenon only.
Yeah, exactly. So that's a really great question. So the way that we can describe, so first of all, it's not easy to understand if the equation is correct or not, but what we can do to some sense evaluate it is that we have some like validation parts that we can evaluate on that, like more general like outer domains that we can see if this equation like is correct or fits well for this one, and also fits for other several like variations. That shows something. And another aspect is that the hope of symbolic regression is that find something, but we rely still on like scientists to evaluate and like validate this. So that's also another part. So there have been some of works specifically in molecular dynamics or in cosmology, and they're all rely on this like aspect. So they have all these additional like either validation sets or different like simulations that they need to be initialized with these equations. And what they do to validate if the equation is better or not is to feed this newly found equation to this like simulation or to these like validation sets and see if it works better than all the previous works. And sometimes it's much better. That's why, I mean, generalizability like happens in symbolic regression.
Okay. All right. Thank you.
Sure.
Are there any other questions for the speaker?
Yeah, may I? This is Kostas Sietos from the University of Naples. So following up actually Panos' question about interpretability, because you put this in comparison with, let's say, black box neural networks. What about, you know, there was a fuzzy logic has been developed for approximating and constructing interpretable, let's say, regression functions. How about that?
I'm not very familiar with fuzzy logic actually. So
I mean, it's another way of constructing interpretable. Yeah. On the other way, you know, a polynomial expansion, you can see the function, but it's not interpretable, right? At the end.
Yeah.
Yeah.
So exactly. So polynomial. So let's say we can't even do like linear regression or higher dimensional regression, like polynomial regression for the task, and we can do either underfitting or overfitting. So the problem is that that final equation is first not interpretable because we may find if we have like let's say 200 points, we can have a like 200-degree polynomial that fits the data perfect, but it's not generalizable and it's also not interpretable. So the hope is that we do this for nonlinear like equations that are not easy to be solved with like those kind of like linear regression models. So we have these different like nonlinear operators in mathematics, like trigonometric function, exponential, logarithm, all of these. And we see these in the like many physical systems. And the idea is that can we find a simple equation that fits the data well and gets this kind of form? And if so, we can then evaluate it to see if it's generalizable or if it can like be like validated into the other outer domain distributions. So that's the hope of like symbolic regression.
Okay, great. Thanks.
Are there any other questions? So with no more questions, it's time to close the session. Thank you so much, Kazem, for your great talk and joining us today. I hope everything you're welcome. I hope everything have a great weekend ahead. Bye.